Hi there, this is session 33 of programming from the very basics using Python. In this session, I will talk about the built-in constructs called map and filter, which were actually functions in the early era of Python, but now they create their own type. I'll talk about that and also talk about some reduce helper functions which are built into Python after I give you a detour on reduce function and tell you the most common use case for them and the built-in helpers that are readily available that you can use in your Python code. Now, first I should talk about what map does. Map and filter both were, I would say, inspired from functional programming languages. You'll find them in a lot of functional programming languages, like Lisp and dialects of Lisp in the early era. And Python sort of got that kind of code to support functional programming features. But should you use map today? This can be debated. I will show you the use cases for them and I'll show you the alternatives and you can make up the decision for yourself on where should I use map and where should I use alternatives for it, which are comprehensions. Now let's talk about what map does. Now let's consider a list that I have here. Let's say I have a list of numbers. Let's say take some small numbers here. 3, 2, 6, 7, 8, and okay, I think I put a comma there. Dot there, sorry. 8 and maybe 5. I just have a list of numbers here. I use small numbers in this case. And I want to square all these numbers. By now, you should know that if you want to square these numbers, you could have done it with comprehension. But in the traditional versions of Python, before comprehensions were available, the way you do that is by using map. Map was a function until Python 3. And this is how it works. So I can just type b is equal to map of, I can use lambda x colon x into x followed by a. The moment you call map should be treated like a higher order function. So the first argument to this would be a function itself. In this case, I use a lambda expression as a substitute. So basically what this does is this will create a function that when given an argument that's x, it's going to return out the result of this expression, which is the square of the number in this case, x into x, right? Assuming it's all numbers. And it works on this data, which is the collection that you pass on here. This can be a collection or any iterable object as long as the lambda expression doesn't fail. So in this case, it works with numbers. So if I try to run this, in very old versions of Python, if you use Python 2, you will get a list of all that transformation being done. But now you get a map object. This map object is also a generator. Just when I talked about generators, I told you, I would tell you that many iterables that you find in Python other than collections, almost all the iterables other than collections that I've seen, they implement a generator pattern, which means that they generate values on the fly when you start iterating over them. So only when I start iterating over B, you could see print V here. And maybe I'll just use end is equal to space in this case. You can see this 3 is transformed to 9, 2 is transformed to 4, 6 is transformed to 36. So that's why you see this is called as a map operation, right? Like in set theory. So what does it do? There's a one-to-one mapping between the input collection and the result. There's a one-to-one mapping. 3 becomes 9, 2 becomes 4, 6 becomes 36, 7 becomes 49. There's a one-to-one mapping, right? That's why it's called as a map function. So this takes an expression as a lambda expression here, and that expression can be applied. You can also pass a function to it. Any function that you create can also be passed on here. If you're doing something more sophisticated, which involves more statements than a simple expression, then it'll just transform that by applying that function being passed as a first argument to the collection that's being passed as another argument. And this result that is provided, in early days, map used to do that work immediately, just like list comprehensions do right now. But the current version of map from Python 3 works more like generator comprehension. So you could say it's a replacement, or you could say it's an alternative for generator comprehension. But if you want a list as the outcome, you can always type list of B. Or you can also have it in a single liner. Let's say you could rather have said B is equal to list of map of You could also use a tuple. It'll work even when you use tuple of map also. So you get this. In the traditional Python world, if you've been using Python 2 series, let's say Python 2.7 or 2.6 or 2.4, all these versions, so you don't have to use list constructor anyways. Map used to return a list, but now they made it more efficient. They made it more like an alternative for generated expression. So it's a lazy mapper. It maps lazily. So the moment you start iterating over the result of map, that's where it starts computing one after another as you keep iterating over it. Just like what I talked about, generator comprehensions, right? Now, there's also another function or construct, I would say rather, called filter. Map does one-to-one mapping. Filter, as the name suggests, filters out items from a collection. So if at all I have a collection that's got all kinds of values in here, let's say 45, then I have hello, then I have, let's say, 5.6, then I have, let's say, none. Maybe I have a tuple of something else, let's say A and B, followed by another number, let's say 32, then 78, then I have false, then I have, let's say, maybe 2.3, then 12. Now I have a very heterogeneous collection here. It's a list of different kinds of items. Maybe what I want to do is I want to extract all integers alone from this. I want to extract only the integers. I want to skip out everything else, even the float and boolean. I want to skip all them out, all of them, right? If I want to do that, what I can do is I can use filter. So the way I do that is I could just type b is equal to filter of lambda x colon. I could just use type of x is int. I'm specifically checking if it's an integer. If you want to check for any arbitrary number, you know how to do that. One of the ways is using the generalization technique. You need to import from numbers, import number, and then check if is instance of x is number. You can use that kind of an expression, right? So I can just type a here, and what you get here is also a filter object. Again, this is a lazy filter. It's like a generated expression, which means that only when you start iterating over this particular object, the filter object, it starts applying this expression, starts searching for element at a time, and then returns out as per need. So if at all I want to get it as a list, you can always type list of filter of lambda, this particular lambda expression. As you can see here, this looks quite redundant in terms of features. The same could have been accomplished by simply using comprehensions, right? So if at all I want to show you how this map can be done, simply using comprehensions, I could as well have done it as c is equal to list. I don't have to use list. I can just use square bracket. And because I want to square all the numbers, I can just say x into x for x in a. And this gives me the same result as map. Really no difference. They both are functionally equivalent. So you can either use the comprehension expression, or you could use map. Both will work, right? Now you might ask me why they have these two forms of doing things. It's just because of the mindset of the developers. As I told you that Python is very welcoming for developers with different kinds of programming style and programming idioms that they have been following. So if you are a programmer who comes from backgrounds like functional programming language like Lisp or their dialects, right, Clojure and others, you might find more comfortable using map. And Python used to have map from the early days, from the 1.x days, I can remember. So maybe 1.5, I believe. So they had it from the much early days. So they just retained that to maintain that essence for such programmers. And you have a lot of legacy code that might also be using map. You want to maintain that compatibility, and that's why it exists. Comprehensions arrived sometime during Python 2, I think Python 2.4 or 2.5 perhaps. It started from there and improvised over time. Initially, it started off as list comprehension alone, but later on they made sure that almost every built-in collections, most of them, can be generated using comprehensions. And by the time, I guess 2.6 arrived, I think there was a generator comprehension that also came up. I think 2.6 or 2.7 they introduced this, and it's been there, being followed. So yes, there are people who like to live the legacy way. Map is suitable for them. There are a lot of arguments by people. They say, oh, map looks more structured than comprehensions. But let's look at it. I'm just going to show you the problem with map if you look at it. So if I want to use, let's say, not just map, but map and filter together, let's assume that I have some users, and let's some users here. Let's assume that, or I can take this example. This one itself should be good enough. Let's take this. Let's continue with this. Let us say that I want to filter out all integers from this collection, but I want to store their squares. I want to filter out all the integers and transform them to their squares. I want 45 square, 32 square, 78 square. So there's a map and filter involved. If you want to do it the traditional way using map and filter, the way you accomplish this is this way. Say b is equal to, first I need to use, I need a list. So I'll say list of map of lambda x colon x into x from the filter of lambda x colon, I could just say type of x is int, okay, is int, followed by a, close parenthesis, close parenthesis, close parenthesis. And then you can just say print b. And look at this. Wow. Anyone who comes from a functional programming background, look at this and say, wow, functional goodness. Function, calling a function, ad infinitum. And that's the kind of thing, that's the kind of world they live in. So it might look very appealing to them, especially if you come from backgrounds like Clojure, Haskell, Lisp, right? You might then look at this and say, this is functional goodness. I remember a quote by Edgar Dijkstra. I'm not sure if it's pronounced his name right. It's known for these lot of interesting computer algorithms. One of them is the shortest path algorithm. I guess you know that. Dijkstra's algorithm. Very popular. And he had made this interesting quote. I'm not sure if I'm quoting it right, but it says, to iterate is human. To iterate is human. To recurse is divine. So functional programming logic will use a lot of recursion, function, calling a function. You take a function as an argument, decide how to call it. That's how it is. But now, we are not like gods. We are human beings, not divine. To iterate is human. If you look at this code, wake up tomorrow and look at this code. List of map of lambda x colon x into x. Oh, what does filter do? Okay, go back to filter and you take values from a and you, okay. It takes some time to really figure out what this code does. That is a reality. I'm going to show you how the same problem statement can be solved simply using comprehensions. I could do the same thing by using c is equal to, what do I do here? I want the square of the values. For that value, I'll use x just because I use lambda x here. So I'm going to just use the same consistent, let's say, variables in here. X into x. For x in a, if type of x is int. And now try to print b, print c. Both give you the same output. You can see the same output from both of them. Now tell me which one is easier to understand or read. Is it this? Or is it this one? And this lets you make up your mind. So almost in all circumstances when I had to think of using map, I was a user of map and filter in my early days. When I was using Python in the Python 2 time, I was still trying to get a hang of comprehensions in my early era, the 2000, mid 2000 time frame. I was, I think 2006, 7, 8 during the time frame when I was toying around with Python. So map and filter was quite comfortable for me. I was using it with lambda and I should show off and boast, yeah, I can use map and lambda and filter and all that. I could tell people, boast off to people that I am an advanced programmer who knows all this stuff. But over time, when I started looking at comprehensions, I thought every single thing I could do with map and filter can be done with comprehensions and the code still remains lightweight and easy in your eyes. You can see this and say, oh, okay, I want the square of the numbers for that number in A if type of that number is an integer. Readable. compared to this. So in my opinion, if you do have a lot of code base which uses a lot of map and filter, you can try and see and refactor the code and try and switch them to use comprehensions. I'm not sure if it'll give you any kind of performance benefit today because map and filter both are sort of similar to comprehensions. There was a time when I used to argue and say that, oh, map is going to be slow. I'll tell you the reason, because there's a function here. In this case, there's a function involved. And there's a function call over it here. And you avoided the function call altogether by just putting in expressions here. So if you really want to time it, I can also show it to you. Let me take this, time both of them. So I can just it's out below here. I can just say percentage time it and paste this code. And I'll also do another cell. Like I need to do another cell in this case. I'll also use percentage time it and use the comprehension variant. Note that both returns a list. So I'm going to make it fair enough. So if at all, some people say, oh, you're getting a list with map, it's cheating. But yeah, I'm using list comprehension. The equivalent is list of map. But maybe if you want to compare map without a list, then you have to compare with generator expressions. I don't think there'll be any difference, right, in that case, because it's just going to generate on the generator. You have to iterate over it ultimately, and that's what you need to instrument. But now I'm going to run both of these and show you with time it here. It's going to run a couple of thousands of iterations. That's what this time it magic does. But it takes about 1.1 microsecond, give or take 33.1 nanosecond per loop, and it ran about 1 million iterations, 1 million loops, 7 times. So totally 7 million iterations were run. 7 runs, 1 million loops each to get this outcome, right? To get the averages correctly. If we try running this with the comprehensions rather, there is a good enough performance benefit in this case. So it makes sense to use comprehensions. But the reasoning is because whether you like it or not, you just can't pass an expression to map. You need to wrap it up in a function, the lambda expression, and pass it on as an argument here. But for simple expressions, you can use an expression as is here, and that is what has led to its benefit. In fact, I remember back in the Python 2 times, I used to see a very steep difference between map and time it. Map used to be quite slow in Python 2 because it always returns a list, and I think it had a little bit of slower implementation. So it used to be at least about 3 to 4 times slower than using comprehensions. But I think in Python 3, they optimized map, they optimized the for loop itself in Python. There are a lot of optimization that's gone into the language design, I believe. So I think you don't see that kind of a strong disparity. So it's still slower here. But maybe if at all you make a function call in here, rather, if at all, so instead of telling x into x, if you just call a function like square function or something, then you will see almost the same performance. So performance wise, I would not argue that map is always slower. It all depends. If your comprehensions does not use simple expressions but leads to a function call for every single time in here, then obviously there's no difference. But still, from the readability standpoint, I still prefer using comprehensions, and it's more cleaner, especially if you want to do multiple things like map and filter together. You can rather look at using comprehensions. So map and filter is there for legacy reasons, in my opinion. There could be very, very corner case scenarios where you're building purely functional programming kind of style in Python and you want to refer to map. Map could be passed as an argument or something else. Maybe that could make sense. But I would still contend and say maybe you can formulate generator comprehension and pass it as an argument. That also would work. So these are my thoughts. So just note what map and filter does. These are just older equivalents of comprehension, the mapping and the filtering comprehensions, right? Map is like just doing x into x for x in A. That's it. But filter is like also adding an if clause that is processing it. That's the only difference. It filters out items based on a criteria. Now, this is something you should know about map and filter. The next set of things I should talk about, next set of functions I should talk about, there was one function, which is a built-in function, all the way till Python 2. I mean, Python 2.x, I would say. And later on, when I switched to Python 3, I saw the function sort of vanished. It's no longer there. So wonder, I was using it. Where did it go? And then when I went and looked into Python change logs and their communication, looks like Guido van Rossum wanted to remove all these functions. When he was releasing Python 3, he was like trying to suggest removal of map, filter, reduce, and perhaps lambda, because lambda is ugly, according to him. So maybe when he suggested removing it, I think the entire community sort of like said, no, 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 we want it, we want it. So reduce alone was removed. It's not actually removed. It's moved. It's moved rather to discourage its regular usage into a module called built-in, into a module called functools module. Sorry, functools module. So if there's a module called functools, I'm going to use it from there. It's called, you'll find a lot of functional programming related features in a module called functools. Functools provide a lot of interesting functional programming features like implementing partials. But there's some interesting things I liked in functools is LRU cache, amazing feature to use. I'll talk about that slowly. It's a decorator, of course. And there are a couple of others, right? You can see that. And one of them is reduce, just in case you need to use it. But the argument, avoid using it. You can stick to using good old for loops instead of using filter, because that's more readable, right? My opinion. But I'll just show you what it does. From functools, import reduce. Now, some of you might be wondering, why am I covering all this in the basics? Because when you start practicing Python and Python code, and then when you start looking up production code, unfortunately, not all production code is 100% Pythonic. It's difficult. The concept of Pythonic is a very subjective thought, and be also biased. What I think is Pythonic may not be the same that's shared by others. It's possible. No, I want to use reduce. I feel that's Pythonic. Somebody might say that. Somebody might say I use map. I still say it's Pythonic. It's been there from Python 1.5. Why change? Yeah. When you start reading such code, you need to understand what they actually do. And that's the only reason I'm covering these things, right? So I'm going to show you reduce here. So you just say reduce of, what does it do? Well, yeah, let me show you what reduce does. Let me just take a list of numbers again. Let's say just a list of numbers. So I'm just going to keep it simple. I'm just going to make it a 10, 20, 30, 40, 50, 60. I could have generated with the range, but it's fine. A couple of numbers. It's a list of numbers. So let's call this values equals this. And now I can do this as result is equal to reduce of. I create a lambda expression, and there's an interesting one. This lambda expression takes two arguments. That means you need to pass a function that takes two arguments. So the first argument should be a function that takes two arguments, and the arguments are x, y. I'm just going to represent as x and y. First argument, second argument. And what this would do, should return a value, and the value I'm going to return is x plus y. And then I'm going to pass values as the argument to this. Now, if you try to print a result here, if you don't know what that number is, it's a sum of all these numbers. So if you want to compute a sum, you want to derive a sum of a collection of numbers, one of the ways you can do it is, rather than writing a nice iterative for loop, you can use reduce. How does reduce work, you might ask me? I'll explain this. Okay, this requires a little bit of focus. Let me show you what it happens. When you call reduce off, when you call this pass on a function which takes two arguments and a collection like this, what reduce does is, the first time is going to take the first item of values, pass it on as x. Second item is passed on as y. So lambda expression gets 10 and 20 passed on as x and y. And what does this do? It sums it up. 10 plus 20 is added or returned. That's 30. Now what it does, it takes 30, the written value of this lambda, right, is fed back as x. The written value is fed back as x. The next value is passed on as y. Now 30 plus 30 gives me 60. Now 60 is passed back as x, and this 40 is passed back as y. And the cycle repeats. As the name suggests, reduce reduces a collection to a single value by using any algorithm here. Maybe you want to get a cumulative product, not a sum. I want to get a complete product of, not cumulative, complete product of this. I can use x into y. It'll become 10 into 20 into 30 into 40 into 50 into 60 into 70. So you get a big number, right? So you can do anything you want. But then it's a very common use case where you want to sum up values in a collection. One way to do it is very iteratively, where you actually say total is equal to 0 for value in, for v in values, total plus is equal to v, and print total. That's one way to do it. But this is a functional programming approach to compute this. If you work in the functional programming world like Lisp and Haskell and so on, this is how you do it, rather than using iterative logic, right? This is a very common way to do it. So to explain, to understand how this flow works, another way to say this is, instead of putting a lambda expression here, I will create my own custom function here. Let's call this as, testfn for now. Keep a simple name. And this particular function, testfn, let's say it takes x and y as the argument. And here I'm going to print testfn. I can just call this as invoked testfn of the actual arguments. I'll pass x and y. What is passed as x and what is passed as y. And here I'm just going to return x plus y. Now, when I run it this way, you can see when I execute this, you can see what happened. First, testfn was called with 10 and 20 as its argument, these two. What testfn returned, the value 30, is passed on as x, and this 30 is passed on as y. Now 30 plus 30 is 60, so 60 is passed on again as x, and 40 is passed on as y, and invoked. And now testfn gets 60 and 40 as x and y. 60 plus 40 is 100, 100 is passed on as x, and this 50 is passed on as y. And the cycle repeats until the collections run out. Ultimately, what is returned is accumulated, and 210 plus 70, the final accumulation that you get here, 280, that is a final result. This is a reduce function. This is what reduce does. You can put any function that helps in reducing items by taking successive items and performing some operation. This is a sum operation, right? There's another use case for reduce, is mostly used for finding out the smallest of a collection or largest of a collection. I'm going to show you that. Again, just like values is equal to, this time I'm going to use some random numbers. It's 56, 34, not a string, sorry. 56, 34, 12, 78, 43, 39, and then 15, and then 24, then 22. Yeah, it's sort of random numbers that you see in values. Now from this particular values, which has got some random numbers in here, I want to find out which is the smallest and which is the largest. So I can just use small equals reduce of lambda x comma y colon x if x is less than y, else y, followed by values. And I'm going to print small. It's found out that 12 is the smallest of this collection. How did it work? The ternary expression does all the magic, right? So given 56 and 34 as x and y, what this expression, what this function, the lambda expression will do, it'll return the smallest of 56 and 34. Smallest of two numbers, right? Return x if x is less than y, else return y. It's pretty obvious. So between 56 and 34, what is the smallest? 34 is written because this condition is true. This x is less than y is true, so x is written, which is no. Actually, 34 is y, right? So this condition is false. 56 is not lesser than 34. So it returns y, the smallest of two. 34 is written. That value, 34, is fed back as x this time to this expression, and y will be 12. Now between 34 and 12, which is the smallest? 12 is the smallest. Pass on 12 as one of the argument. Pass 78 as another argument. Between 78 and 12, which is the smallest? 12 is the smallest. Pass on 12 as one argument. 43 as another argument. So this is what you do. If you try to do these kind of bubble sort, the fundamental, one of the part of the bubble sort is this, right? So most sorting algorithms, you do that. So if at all you want to find out the big number from here, which is bigger, I can say big is equal to, you can just change the expression a bit. It's almost similar. So lambda x comma y colon x plus y, and then not x plus y, sorry. X, if x is greater than y, else y from values. And this will give me the biggest. 92 seems to be the largest. That's the last one that is there here. Now, these are the three common use cases, practical use case for reduce. Finding out the smallest, finding out the largest, getting a sum of list of numbers, right? And in Python world, they realize this is a very common pattern that you'll find in a lot of code. So rather than writing this complicated code of reduce, I say this is complicated because for newbies, for new, if you're just hanging on with me with my videos so far, even at this moment, you'll think, oh my God, this guy started with something very small, very simplistic, and now he's gone all the way to reduce lambda and all this stuff. My brain is hurting. You find if you feel that way, you're not alone. It takes some time to assimilate this, but then you really don't have to use this. That's the best part. Then why do you talk about this? This is to give you some exercise to your brain. That's it. That's the real truth, right? So if at all I want to do the same thing, sum, min, max, three built-in functions exist which are called as reduce helpers. So actually there are three, there are 5 of them. I'll just show you this. I'll just type sum of values. Sum is a built-in function, by the way, and it works as long as values only contain numbers. They must be addable. You should be able to add. And yes, you might think, can I pass sum of strings or sum of list of strings? It's not going to work because this sum internally starts with 0. Takes the first value of 0 and tries to accumulate values into it. So 0 plus a string will fail, right? That's something you should know. Should be homogeneous, integral data, right? However, the min and max are a little flexible. They must be comparable objects that can be compared. You should be able to use less than and greater than and compare their equality, right? Or the order. So you can technically have a collection of strings and find out which is the smallest string and largest string based on the lexicographic ordering. All that can be done if you want to, but they must be homogeneous. You cannot compare a string with a number, right? So that's things you keep in mind. So you say print sum of values, min of values, and max of values. These are the built-in functions which are basic reduce helpers. 393. Was it 393 here? Oh, I used a different number. Okay, all right. I used a different number here. That's what I wanted. It was 280 in this case, but I used a different number here. So I'm going to put this all together. So I'll just even put the sum function here. Okay. So I think I'll just say total is equal to reduce of lambda x comma y colon x plus y from values and print total. 393, 1292. But the same thing which I did using this complex reduce expression can be simplified by simply using min, max, and sum. 3 built-in functions. These are functions. They're written a number, right? It's not some things like the iterable helpers I talked about. They're written some constructs. They are their own types. Nothing of that. They're just written numbers in this case. Min and max is quite flexible. It works even with strings. If at all you have a collection of strings, you want to find out which string comes in the sort order, the earliest string, the smallest string in the sort order, right? Or largest string in the sort order. You can use min and max for that. But sum is exclusively for an iterable of values. So remember, the values need not have to be a list. It can be any iterable object. It'll work perfectly fine. It can be a tuple. It can be a range. Maybe I want to find out sum of first 20 numbers. You want to find the sum of first 20 numbers? Sum of range of 20. It works. Simple, isn't it? It could be an exercise. Find out the sum of the first 25 numbers. In other languages, you write some logic, loop, and all that. Python, sum of range of 20. Done. That's it, right? But there are two more reduce helpers. And these are convenient in certain use cases. And they are pretty obvious. It's called all and any. So I'll just show you what it does. Let's take values one more time. But just like all of values, what this returns is a boolean, true, if every single item in this iterable passed into all takes an iterable as an argument, it iterates over it, and ensures that every single item it iterates over evaluates to true in boolean context. What this effectively means is if you have values here of numbers, it'll return true if all the numbers are non-zero. In this case, if you have one of the values which is 0, if I have one of the values which is 0 here, you can see it becomes false. Remember, it can be 0, none, false, empty string, empty, or any kind of empty collection, empty list, empty tuple, all of them evaluate to false in Boolean context. If any of those exist in values, return value is false. Maybe you didn't have 0, but you had none. Maybe there's a none value here. This will show up as false. So for all to return true, every single item in the iterable passed as its argument must evaluate to true. Right? That's what you should know. That's what all does. So every single item in here must evaluate to true, only then all returns true. All of it is true. That's what it means. The opposite of all is any, as you might have guessed it. Any will return true if any one of the item in the iterable evaluates to true. The first item evaluates to true, any will stop right there, it will not even process anything else. It uses a short circuit. It will also tell you that all starts iterating over values. If this returns true, go to the next one, returns true, go to the next one, returns true, go to the next one, returns true. The moment this returns false, it stops right there. It doesn't bother processing anything else. It is optimized. The moment it sees the first item that's evaluating to false, it'll stop right there, returns false, doesn't bother with the rest. Any on the other hand, if the first item evaluates to true, it stops right there. The first element evaluates to false, second evaluates to false, third evaluates to false, fourth evaluates to false, and the fifth evaluates to true, it'll stop right there, returns true. It'll return false if all items evaluate to false. I will show you what any does here. The same thing, I'm going to copy this. If I use all of values, it returns false. In this case, if I say any of values, it returns true. The reason? The first item evaluated true here. So it doesn't bother even checking the others. It doesn't worry about the rest. If any one item is true, the result is true. For any to return false, every single item in a collection must be false. Let me show you all the built-in data of built-in types rather, or them that evaluate false here. 0, 0.0, that's a floating point version of 0. 0 plus 0j, there's a valid complex number where both real and imaginary is 0. You could also have things like, say, empty string or even empty bytes object, or it could be a empty tuple, empty list, empty dictionary, empty set, and none and false. So run this. None of these items are treated as true in Boolean truthiness or Boolean context. So when you see that, this will evaluate false. If any one of these items, let's say I put a value in this list, like put a 0 here, what do you think is the outcome? A list, even if it has a 0 in it, the size of the list, the length of the list is 1. The list has one item. For a collection, if it has even a single item in it, it's going to be true. So you can see that it throws true here. It returns true, right? So this is what all and any does. To summarize, the built-in reduce helper functions, which does reduction. We also call them reduction functions, which reduce a collection to a single outcome, single value. What are they? Built-in functions. I can say built-in reduction functions. They are sum, min, max, all, and any. Okay, I put built-in, sorry, mistyped. Built-in reduction functions, right? All of these are the ones that you should be aware of. So maybe I'll just make it markdown. So can just make it a markdown object, markdown cell, sorry. That's it. So this pretty much sums up all these important built-in functions and constructs I sort of skipped for a long time. I think this pretty much sums up most of the features in the built-ins that you'll know. If you want to know what are the built-in functions in Python, one way to find out is obviously the help system in Python, or another way, you can always import a module called built-ins. The built-ins module gives you access to all the built-in features of Python. And when you do a print dir of built-ins, yeah, this goes like this. May not be a good idea. So I'll just do a dir this way. Instead of using print, I'll try to use dir like this. Yeah. Everything that comes up capitalized, most of these are either classes or constants, and whole lot of them are basically errors. We saw type error, name error, value error, index error. What are they? Actually, they're all classes. Every error, there's a class created, and whenever an exception is raised, it's an instance of that error that's created and thrown, right? Raised. So all of these are the classes for the errors that you see here. All of these. A couple of them could be like warnings, like you have warnings also sometimes, assertion warnings. Yeah, I think just put a triple dot here. So let me just try to make it a scrollable item. You can see all of these. A lot of them are built-in functions, types, right? Either they're functions or types. A-iter is async iter to check whether it's a async object. Remember, I used async def in the previous session. You want to check for that, use A-iter. That's the only feature, right? A-next is to get the next, go to the next code path in async iter. So these are newly introduced in Python 3.6. You can see all of these functions. There's something called breakpoint. I'll talk about that when I talk about Python code maintenance. There's a dedicated video or a session where I talk about how do you maintain your Python code. So there I'll talk about a lot of things like annotations, type annotations, testing, how do you do unit testing and doc testing and all that. And all these as part of the Python standard library that is. I'm not going to be focusing on PyTest on that. Just maybe I'll give you a hint on that. And about profiling your Python code and also other things like debugging. I'll focus on that in a separate session, right? Might go to multiple sessions, perhaps we'll see that. All of these you can see. So all of these are the built-ins. And most of the built-ins by now I would have covered. A lot of them. A lot of these are either built-in functions like print and input and len and so on. The many others are types, like say if you look at things like say tuple, list, float, complex, these are types. Some of them, they look like functions, but technically they're types like zip and enumerate and range. We call them as iteration helpers. So you can see all of them in this place, in one place. This gives you a list of built-ins. So maybe from this list of built-ins, I only want to know these things that start with small letters. How do I do that? It's a list, right? So I don't want to print all these stuff. I want to only know the built-in, maybe functions and constructs, right? How do I do that? So you can also write your own code here. I can just say, maybe show up x for x in dir of built-ins if x of 0 dot is lowercase. That will do. You can also use x dot lower, I guess. That also will work. But then this should suffice. You can see a filter. You can see how we can apply a filter, right? There are some interesting problem statements I can also talk about when I talk about comprehensions, because I want to talk about that. Maybe I skipped it. Let us say that I have a collection like this. Let's take this values itself, which maybe, yeah, this will do. Let's take this. Let me remove this none. Maybe add more numbers. I'll just try to add more numbers. Let's say 27, 35, and 52, then 63, and 42, then 21, 92, and 88. Try to make it a little bigger. That's it. Now, I have this collection. What I really want to do is I want to create another result. I want to create a resultant list where for values that is greater than 50, I want to store 1. For values less than 50, I want to store 0 in the resultant list. What I want is a result. I'm going to tell you what I want the result is. A list. You can see that 56 is greater than 50, so I'm going to put 1 there. 34 is less than 50, 0. 12 is less than 50, 0. Then for this I want 1, 0, and 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0. I want the result like this. What I mean to say is that I want a result where for value greater than 50, I want to store 1. For value less than 50, less than or equal to 50, less than or equal to 50, I want to store 0 in the resultant outcome. How do I do that? Think. I want you to try it. Maybe you can pause the video and you can try it on your own and let me know if you got it. Well, consider this. What kind of an operation that you do here? Obviously, this is a transformation. You're transforming source to destination. Obviously, you need comprehensions. You could also use map and filter and all that. But fine, I'm going to stick to comprehensions for this. What kind of comprehension should I use? Should I use a map or should I use a filter? Think. But at a certain glance, you may think it's filtering because you're filtering out elements that's greater than 50 as such. But no, the result is not reduced in size. It's a 1-to-1, right? There's 56 becomes 1, 34 becomes 0, 12 becomes 0, 78 becomes 1, 27 becomes 0. When you see a 1-to-1 mapping between the input data and the outcome you're expecting, right? It's not a filter, it's a map. To know if clause on that side is required. So how do you solve this? How do you create this? One way to do it. Yeah, one easy way to do it is maybe, I thought I could make it more complex, but it's very easy. I could just say result is equal to, I could just say x greater than 0, right? X greater than 0 for x in values. So when you print result here, which shows up as, oh, x greater than 0 for x in values, everything is true. Oh, why is that the case? Oh, I said x greater, not 0, sorry. Sorry about this. Greater than 50, right? Greater than 50. Everything is greater than 0 in this case, right? Yeah. But this is a Boolean. So if you want to make it an integer, you know what to do. You can always create an integer from a Boolean and you get the resultant outcome like this. This solves it. I think I was not correct in that place here. I think about 0 here. It should be 1, right? The result is this is what you get. But what if I want to have a string where I want to say small and big? I want to print a message called small for values lesser than 56, less than or equal to 56. I want to put small instead of 0. I want to print, I want to store large as a string. I want to store a value called small and large based on the value in the source list. This is where you can also use this technique to do it. I could just type maybe small if I could say x is less than 50, less than or equal to 50, or maybe it's better to type large if x is greater than 50, else small for x in values. Now look at this outcome. You will see a list. I forgot to print result. Sorry, print result now. These are some practical use cases. These are some practical use cases. You would actually use it. Sometimes you want to categorize. You want to say, I want to create some kind of slotting where I want to say small, medium, large, extra large. Then obviously you cannot. I don't want you to use this kind of ternary expression. You can use ternary expressions, but you have to nest it. It gets extremely complicated. Don't do it. Create a function. And the function based on the range of argument would either return small, medium, large, or extra large. So maybe I can create a dedicated function for that. Let us say I want to consider values below 25 as small, 25 to 50 is medium, above 50, 50 to 75 is large, anything above 75 is extra large. So I'm just going to print maybe small letters, let's say like in like you get on t-shirts in, I think in India at least it's very common. You see a S or a M or a X or a, sorry, it's a L or a XL. So I get that. So I can get a function for doing that. In this def, I can just provide sizes, let's say, of V. And here I can use if condition, right? I can say if V is less than 25, or it can say less than or equal to 25, return S. And if V is less than or equal to 50, return M. Oh, not X, I think V. And if V is less than or equal to 75, I'm going to return, I'll use all the capital letters for now. So M, S, and M for medium. And here I'll just type return L, else. Return XL. I define a function like this. Now, your offline exercise is to see how you can make this more efficient. You see a lot of ladder-like if-elif constructs. I personally don't like it. When I see something like this, I want to think of optimizing it better. I want you to put your thought process and then try to come out with a solution that is more optimal than this one. Right? That's your exercise. I want you to try it out. If you got an answer, just post it on comments or you can send it out to me by email. Right? But for now, I can use this right now. But I can just directly say here, sizes of X. And this else clause and all is not required. So it's a simple map comprehension that you see, list comprehension that applies a map. And try running this, you get a result. You can see how I'm doing a transformation here, right? You can see how I'm doing a transform here. So all these are interesting use cases for applying comprehensions. The same thing, if you're interested, you can try doing it map. It's pretty simple. If it's just a list of map of lambda x colon size of x and whatever. I don't think you need lambda here. Map of sizes, and so you can also do this with lambda. You do this with map, right? If you want to try the same thing with map, how do you do it? You could just use result is equal to list of map of sizes this time, and then type values. In this case, some of you might argue and say, oh, map is so simple. No need of for x in values. You can just say map of sizes, comma values, and it works. Maybe there are some use cases where map might look a little simpler, but beyond this, I would think twice before using it. Yeah. Right? With this being done, I think I will finish this video here. So I think I covered all the interesting functions which is related to map, filter. I told you about the reduce function that is there in the built-ins module. No, not built-ins. It's in the functools module, which you need to explicitly import to use it from Python 3 onwards. Generally discouraged. So if you think you need reduce, you're better off using good old for loops to solve a problem. The most common use case for reduce is like finding out the minimum, maximum of correction of values, or finding out the sum that's anyway available as a built-in, and all and any functions. These are the things that are available in the built-ins, right? If you really like all the concepts I covered in this and you found this video informative, and if you also, I would recommend you to also watch the other sessions if you have skipped and by watching the session directly, in case you want to look for other features or other aspects of Python that you want to learn. And if you really like this video, do hit the like button and do subscribe if you're not already subscribed, and this will give me more encouragement to make more videos like this, right? And thank you very much. So hope to meet you in the next video.